Hello, ladies and gentlemen. Welcome back. Next up, we have the session, Demystifying Quantum. Let me introduce to you the speakers. First up, we have Dr. Radia Perlman. Dr. Perlman's work has made a profound impact on how computer networks work today. It enables huge networks, like the internet, to be robust, scalable, and largely self-managing. Her technology also transformed Ethernet from a technology that could support a few hundred nodes within a building into a technology that could support networks of hundreds of thousands of nodes. She has also made important contributions in network security, including robustness, despite malicious trusted participants, assured delete, key management for data at rest encryption, DDoS defense, and user authentication. Dr. Perlman is currently a fellow at Dell EMC and has taught as adjunct faculty at MIT, Harvard, and University of Portland. She wrote the textbook, as you all may know, Interconnections, and co-wrote the textbook Network Security.
We also have Mr. Charlie Kaufman. Charlie is a well-recognized industry expert in the fields of computer network and distributed application security. He currently works with Dell EMC. He's responsible to determine, understand, and prioritize any security vulnerabilities and customer-requested security features in EMC's VNX product line. He was also chief security architect at Microsoft Azure, Microsoft's cloud computing service and product offerings. So before we welcome Dr. Perlman and Mr. Kaufman, at the end of their Q&A session, we will be picking someone to win a signed copy of the book that they co-published. And Dr. Radia and Charlie will personally be signing this book. Yeah, so make sure you ask some difficult questions. The most difficult question for them, they will give this book to you. Thank you.
Okay, so let's see. This doesn't necessarily have anything to do with blockchain, but quantum is a buzzword and everyone finds it terrifying. And so hopefully this will explain exactly what it is. So yeah, there's a lot of hype and a lot of wild speculation about quantum. And so the first half of this thing will be sort of understanding quantum computing, you know, what exactly is it? And the other half we'll be talking about new public key algorithms that will be safe even if there might be quantum computers. And we'll be doing tag team. We haven't decided quite which parts, which one of us will do, so, you know, whatever.
And somebody runs out of voice, the other person will play tag in.
Right, and feel free to, you know, at least the physical audience, feel free to ask questions during it, because I don't want anyone to get lost. But yeah, the questions should sort of have something to do with the talk. So yeah, we'll talk. So this is interesting because the slides are behind me. I haven't I didn't.
Right, I expected there'd be a copy up there.
Right, right. I should have memorized the slides first, I guess. But anyway, so we're going to. Yeah, what's different about a quantum computer than a classical computer? Why is it powerful? What limits its power? And what its impact is on cryptography. And I'll talk about kind of the two algorithms that you hear about, Grover's algorithm and Shor's algorithm, and I'll explain what they are and how they work, well, how Shor's algorithm works. There's only a limited amount of time. So they're both really cool, but not enough time to talk about both of them. But all of this is in the book, yeah, which we co-wrote. And the second half will actually explain some of these algorithms. So you hear these terms, oh, it's a lattice space, it's a multivariate, you know, we'll explain what that means and give some intuition into at least some of them. So common misconceptions about quantum is any program that you could run on a classical computer would run a bazillion, jillion times faster on a quantum computer. And I'm saying misconceptions. This is not true, but that's what a lot of people believe. And we know all sorts of problems that would be solvable if only we had a quantum computer. This is also, well, you know, we'll see. Okay, I'll remember some of the other misconceptions I have on the slide, which is that after somebody demonstrated quantum supremacy, it's like all over for classical computers. From now on, you know, all of our laptops are going to be quantum laptops. Another thing that people say is quantum computers break all of cryptography, and that's absolutely not true, as we'll see. It's only the public key algorithms. Something else I hear people say is that quantum computers can factor prime numbers.
We've got some slides back.
Okay. Yeah, this one is not on the slide. But yeah, so many people say that quantum computers can factor prime numbers, and this sort of drives me crazy. Yes, a quantum computer can factor a prime number, but I can do it in my head. You know, as long as you know the number is prime, it's factored. So what a quantum computer can do is actually factor non-prime numbers into their primes. Okay, and so anyway, all of these statements are false, and hopefully we'll explain it in the talk. So, a quantum computer is not a faster version of a classical computer. It's different. So what is it if it's different? You don't need to understand quantum mechanics in order to understand the rules for a quantum computer. You know, it might be interesting to understand how quantum mechanics comes out with these rules, but for now, just believe me that these are the rules that a quantum computer can do. So it's important to understand these rules so you can know what kind of algorithms would work on a quantum computer versus a classical computer. So a classical computer stores information in bits, where a bit is either a 0 or a 1. A quantum computer stores information in qubits. So great, we've given a different name to this thing. But what's the difference between a qubit and a bit? So, yeah, so there's three very weird things about qubits. One of them is superposition. So a qubit isn't just 0 or 1, it's some mixture of 0 and 1. It's simultaneously 0 and 1, and so this is called, both values are superposed, so it's holding both of them at the same time. A second one is measurement, and I'll talk about each one of these. Oh, okay, now I can see the slides too. Yeah, measurement, well, we'll have slides about each one of these things, and entanglement. So what is superposition? It's the idea that it's simultaneously holding some amount of 0 and some amount of 1. So the state of the qubit is how much 0 and how much 1 it is. So it's not just, I mean, the state is actually a very complex thing because it's, you know, sort of there's an infinite number of states that a single qubit can use because, you know, it's actually a complex coefficient of how much 0 and there's kind of an infinite number of numbers. So, yeah, so the state of a single qubit is sort of how much 0 and how much 1. And how, you know, sort of how tall that thing is, if there's more 0 than there is 1 in that slide, determines the probability, if you read it, whether you'll get a 0 or a 1. Superposition The state of the qubit, the horrible notation, but everyone uses it, so you might as well see it, is kind of a coefficient of 0. How much 0? So it's alpha is the coefficient of 0, and beta is the coefficient of 1, and the coefficients determine the probability of, if you read it, it determines how much of it is 0 and how much of it is 1. And it would be sort of more intuitive if it was a probability, like it's 70% 0 and 30% 1. But there are actually what's called probability amplitudes that you have to square them in order to figure out what the actual probability is. So the two coefficients, alpha squared plus beta squared, is 1. And because they happen to be complex numbers, it has to be the absolute value of alpha squared plus the absolute value of beta squared is 1. So the probability, if you want to read the qubit, that it will read as 0 is alpha squared, or the absolute value of alpha squared. So this is this notion, the notation, which is that you have a coefficient and then, a that and a that with a 0 in front. It was invented in 1939 by Dirac, and it was kind of before people had nicer, word processing tools, but everyone uses it. So we'll try to make it more readable using color. And if it doesn't make it more readable, at least it'll be prettier. So the state of a qubit, what's the squaring business? Well, it's actually a point on a circle. So if you remember sort of, 11th grade geometry, any point on a circle, it's sort of the cosine and the sine. The cosine is the x-axis and the sine is the y-axis. And if you square the x coordinate and the y, and you square the y coordinate, it'll come out to be 1. So the state of a qubit is any point on this unit circle. Right. But because it's actually complex numbers, it's a point on a 4-dimensional sphere. So, and if you've ever played with a 4-dimensional sphere, any way that you hold it, it's the same sphere. So if you kind of align it so that the complex coordinate goes away, because of the symmetries, it can actually be represented in 3 dimensions rather than 4. Not that this really matters. One thing about superpositioning or superposing values or whatever. To me, I would have said you superimpose values, so the two values are superimposed, but everyone else seems to say superposed, and I asked somebody, why is it superposed instead of superimposed? And he said, well, superimpose is when you get invited for dinner and you stay a month. So anyway. So measurement is the other weird thing about qubits. If you read a qubit, you'll get either a 0 or a 1, but then the other value disappears. So if you read 0, it's then completely 0. So it loses its quantum state and it only becomes the value that you read. So if you read a qubit twice, you'll get the same thing the second time because the other value goes away. So let's say this was the state before, and then you read it. If you happen to read 0, the state afterwards is no amount of 1, and it's all 0. And if you happen to have read 1, then there's no 0 left, and it's only 1. So people following so far? Okay. Entanglement, and the people on the phone, who knows? Can't see your faces. So entanglement is incredibly weird. I mean, the other two properties are disturbing enough, but entanglement. When qubits are entangled, you can't talk about the state of the individual qubits. It's only the state of the group of qubits. So if you had two entangled qubits, the values that they hold is some amount of 0, 0, some amount of 0, 1, some amount of 1, 0, some amount of 1, 1. And if it were 3 qubits, it would be some superposition of the 8 possible classical values that 3 bits could do. So a set of entangled qubits has a state. And if you had 3 entangled qubits, the state will be a superposition of one of those 8 values. And so the way you would represent the state of 3 entangled qubits is some coefficient of 0, 0, 0, some coefficient of 1, 1, 0, 0, 1, and so forth. And if you square all of these coefficients, the probability has to be 1, that it will be in one of those 8 states. Now, what's really weird, if you're not disturbed already, let's assume that you had 2 entangled qubits and you managed to superpose only the 2 values 0, 0, and 1, 1. So the probability of 1, 0 and 0, 1 are 0. So they hold some amount of 0, 0 and some amount of 1, 1. That means that if you were to read the first qubit, you'll know what the value of the second qubit is. If you read the first one and it's a 0, the second one has to be 0. Or if you read it and it's a 1, the second one has to be 1. This is true even after when you entangle them, if you move them very far apart. So let's say that you have these 2 entangled qubits and you manage to superpose those 2 values, and then you separate them so they're really, really far apart on opposite sides of the universe. If you read one of them and happen to read a 0, the other one will also read as a 0. And there's 2 ways this could possibly work. One is that when you read the first one, with telepathy, faster than light telepathy, it tells its friend, hey, I decided to be a 0. And its friend says, oh, okay, I'll be a 0 also. Or before they separated, they kind of made a pact. And the first one said, hey, we're separating, but just letting you know if anybody ever reads me, I'm going to be a 0. And the other one goes, gotcha, I'll do the same thing. Well, they've proven that both of those are false. So I've tried to shake a physicist. I said, fine, I'm willing to believe that both of those are false. Give me any possible explanation for how this can happen if it's neither of the other 2 things. And he says, well, look at this fine math and these equations. It just says that's how it will work. But you're in good company if you don't like this. I don't like this. Einstein didn't like it. He called it spooky action at a distance. And it's ridiculous, but experiments show that it's actually true. So multi-qubit states, if you have a set of n qubits that are not entangled, just to show how it's a much simpler system if they're not entangled, you could express the state of the n qubits with 2n coefficients. For the first qubit, you know how much 0 it is and how much 1 it is. That's 2 coefficients. And for the second qubit, 2 coefficients. So it would take 2n coefficients to express the state of n unentangled qubits. But if they're entangled, the only way you can express it is with 2 to the n coefficients, because you need to have a coefficient of how much 0, 0, 0, 0 it is, how much 0, 0, 0, 1 it is, and so for each of the 2 to the n states, you need a coefficient. So if you had 10 qubits, if they're unentangled, it only requires 20 coefficients to express their quantum state, whereas if they're entangled, it's going to take 1,024. So if you have a group of qubits And if you have n qubits, it has 2 to the n superposed states. We talked about that. So if you have 3 qubits, it holds some amount of each of 0, 0, 0, 0, 0, 1, and so forth. And so that picture here shows sort of all of the possible states, and the height of the bar for each one is sort of the amount of that one. So if you read the 3 qubits at this point, again, all the other states go away. So if you happen to read 0, 1, 0, all the other states go away, and the 3 qubits only hold that one state. Or if you read 0, 1, 1, all the other values go away. But suppose you only read a subset of the entangled qubits. So let's say that the 3 entangled qubits are what's there, and you only read the first qubit, and you happen to read a 0. Well, all the states in which the first qubit is not 0 go away. They're now impossible. But all the states where the first qubit is 0 remain possible, but you have to scale up the probabilities so that the probabilities will again be 1. So that's what would happen if you read 0. And if you read 1, then again, those values go away, and it's all the other one. So yeah, because the probability have to add up to 1, the state can be represented by the point on a surface of a 2 times 2 to the n dimensional unit sphere. And the reason it's twice that is because they're actually complex numbers, so you need a real component and an imaginary component. So superposition is what makes a quantum computer powerful, but with restrictions. So when you compute on a set of n qubits, it's logically as if you're simultaneously computing on all of the superposed values at once. And the output will be that you have calculated the output of each of the possible inputs that are superposed, and then you add up all of the outputs to find out what the quantum state is afterwards. So that it's not as powerful as you might think from that description, because you can't read it without losing the superposition, which is the only thing that makes a quantum computer powerful. And you can't copy a qubit. So these are severe restrictions. You know, like you can't just take any old classical computer program and run it on a quantum computer. And you can't choose which answer you want. When you read it, you get, you know, some probabilistic, you know, depending on the probabilities, you'll get one answer. You won't get all of the answers. So the parallelism, the fact that it's operating on all the inputs at the same time, doesn't give you 2 to the n answers. It only gives you one answer when you read it. So this sounds like a nondeterministic Turing machine, where you're doing 2 to the n things in parallel. But it's not. So, wait a minute, what's a nondeterministic Turing machine? Just for curiosity, who here knows what a nondeterministic Turing machine is? Okay, a few people. That's okay, I'm about to explain it. So, a nondeterministic Turing machine is really just a thought exercise. So for each, what it is that you imagine a computer that every time it branches, it kind of spawns up a separate copy of itself, and it's doing all of these threads in parallel, and whenever one of them gets to the answer, it raises its hand and says, "Oh, cool on me, I know the answer," and you know, right. So. You can simulate a non-deterministic Turing machine on a regular classical machine, but it gets exponentially hard every time it takes a branch. You have to kind of spawn up another copy. So there's a famous open computer science problem, which is that how much more powerful is a non-deterministic Turing machine than a deterministic one? And so the question is P equals NP. P is the set of problems that can be solved in polynomial time on a deterministic machine, and NP is the set of things that can be solved in polynomial time on a non-deterministic Turing machine. And nobody knows whether they're the same or not. It's something they've been arguing about for years, but everyone believes they're not the same, that there are things that would take exponential time on a deterministic machine, but would be solved much more quickly on a non-deterministic machine. And likewise, there's a misconception that these problems that would take exponential time on a deterministic machine would be solvable quickly on a quantum computer. And no, nobody's proven that you can or that you can't, but it would be pretty much as surprising if they, well, which would be, yeah, if they're equal, right, yeah, so anyway. So yeah, okay. Right. Okay, I'm not quite sure why I'm talking. Yeah, so with a classical thing, you operate on bits with gates, like an AND gate or an OR gate. You can do the same thing with quantum computers, but nobody, it's like unbelievably more difficult to build a quantum gate that operates on 3 qubits at the same time. So anything that you can imagine it doing, if you could imagine a gate that takes 12 qubits input, you can build that logically, but you have to simulate it out of 1 and 2 qubit gates. So, okay. All right, so yeah, whether a quantum computer can solve these NP problems, which is non-deterministic polynomial time, is unknown, but it's believed to be no. So maybe I should let you talk for a while.
Yeah, an intuition for this non-deterministic Turing machine is, for example, if you knew that there was a particular 128-bit key that would, decrypt, value A into value B, and you wanted to find out how hard it was, well, on a conventional computer, that would take 2 to the 128 steps. You'd have to try all possible keys. On a non-deterministic Turing machine, you just have to take 128 branches and do it in one step, so it'd be a very fast operation. So a non-deterministic Turing machine would, in fact, break all of cryptography, but a quantum computer isn't nearly that powerful. So how do qubits get in these states? You can have a qubit, if you read it and it's a 0, then it's a 0, and there are gates that you can apply to a qubit to complement it, so you can get them into a 1 state. But how do you get it into these funny states where the things are neither 0 nor 1? So to initialize a qubit to 0, you simply read it. If you got a 0, you're done. If you didn't get a 0, you apply a NOT gate, and that will change the 1 that you got into a 0, and then you're done. To create a superposition, there's a thing called a Hadamard gate. And a Hadamard gate, if you apply it to a qubit that's either in a 0 state or in a 1 state, it'll change it into a state that if you read it, you'd have equal probabilities of getting 0s or 1s. So oftentimes a quantum program will start up by taking a whole set of qubits, setting them to 0, run Hadamards on them, and now you have, 2 to the n possible states, all of equal probability laid out there. Yeah, lots of gates are in theory possible. In fact, things are built out of 1 or 2 qubits. And the analogy is that if you're building circuitry with a traditional computer, yes, you might have a function that's going to take the, going to multiply together two 64-bit quantities, but in reality, you're going to build those out of things that take 2 bits at a time and either do ands or ors or nots on it, or 1 bit and does a not on it, and you're going to assemble it out of those parts. So similarly, when you're doing things on a quantum computer, you're going to act, you just have gates that act on 1 or 2 qubits, but you can assemble them together to operate on a larger set. So yeah, if you want to do something with a bunch, you build a circuit. And just as with a conventional computer, if you can build a NAND gate, which is, takes the not of 2 inputs and then ANDs them together, any possible gate you want to build, any circuit you want to build can be built out of those gates by gluing enough of them together. And similarly with quantum computers, you can get a universal gate set, which is a small set of gates that anything you want to do with a quantum computer, you can do with some sequence of operations with those gates. And so, the exact gates that you build depends on what hardware you're dealing with and what it turns out to be easy to build, but it only takes a small number of gates to be able to become universal. Right. So there's this thing that you can't copy a qubit. So if you have a qubit whose state is alpha of 0 and beta of 1, you might think that you could make a copy of that, but you can't. You could, if you had another qubit, you could XOR the value of the first qubit into the second qubit, and you might think that would create a copy. That would create a copy if if you had a regular digital circuit and you XOR'd something into a value that was sort of initially 0. But with a quantum computer, when you take the qubits, you'd wind up with you wouldn't end up with 2 independent qubits. You'd end up with 2 qubits that were, in fact, in an entangled state that showed that combined them, that had all these if you had 2 qubits that were identical, you'd end up with something that was in this complicated state. But in fact, when you did the XOR, you'd end up with 2 entangled qubits. So they wouldn't be independent and identical, they'd be entangled, so that when you read, so that if you ever read them both, that you get the same answer from both of them. You wouldn't be able to independently pull the probabilities. And that's one of the things that's really important, is that when you set up one of these qubits, if you know that there's a 60% chance of reading a 1 and a 40% chance of reading a 0, you can't sample it 100 times to verify that, because once you've sampled it once, that's what you've gotten. You'd have to go back and rerun the whole experiment to get them into that state again. Okay, so multi-input gates, the people only really build those. Let's see. Right, so when you're measuring the running time of a quantum algorithm, what you're really interested in is the number of these little 1 and 2 qubit operations you need to do, and so that's how you sort of evaluate it. You might build a complicated operation that does a 64-bit multiply, but you have to figure out how many individual qubit operations it's going to take to do that, and that's really the measure of the time. The quantum computers was sort of a weird novelty that nobody cared much about. It was originally proposed actually by Richard Feynman, who noted that gee, given that a classical computer can't simulate a quantum system except in exponential time, does that mean that a quantum system might be able to do some calculation that would be useful to somebody faster than any conventional computer could do it? And this was a subject of speculation for 20 years or so. And the first real progress on it was Shor's algorithm in 1994, where he showed, in fact, that on a quantum computer, you could factor large numbers in polynomial time. And all of a sudden, that caused enormous amounts of funding to flow into quantum computers, because that means it could break the RSA algorithm. And in fact, the generalization shows it can break all of today's public key algorithms. So, oh, right, yeah, there's Grover's algorithm. Grover's algorithm came a couple years later, and it potentially could be used to attack secret key algorithms. However, in the best case of running Grover, it reduces the difficulty by a matter of the square root. So instead of taking 2 to the 128 steps to find a 128-bit key, you might be able to do it in 2 to the 64th steps, which is still a lot of work, especially on a quantum computer where life is more difficult. So this turns out to not actually be cryptographically very important, because if you double your key size, that will more than compensate for anything that's going on there, and doubling your key size is not a tremendously impractical thing to do. So as long as you're using 256-bit keys rather than 128-bit keys, you're very safe, even if very good quantum computers ever get developed. And in fact, when the AES algorithm was developed around 2000, one of the big motivations for having anything bigger than 128-bit keys, because the work to break 128-bit key is truly mind-bending. And the reason why they wanted to have a 256-bit variant is because they anticipated that quantum computers might come along, and they wanted to make sure they were going to be safe even then. So it doesn't really require any new advances in cryptography to cope with quantum computers in the secret key space. It's only in the public key space where we have a problem.
You mentioned hashes, too.
Right, and hashes are the same way, that hashes, a 256-bit hash is as much as you need for any real practical purpose today, but a 512-bit hash is defined, and you might use that in order to continue to be safe even if quantum computers become popular or become successful. So Shor's algorithm is devastating to essentially all of the existing deployed public key algorithms. And that's kind of annoying, but the algorithm and how it works is incredibly cool to look at and analyze. The transitioning to bigger public keys doesn't, in the secret key space that fixes it. In public key space it doesn't. Somebody actually ran an analysis to say, well, suppose we just were willing to make them as big as we had to make them to be secure against quantum computers. And somebody said, yeah, I guess actually, they said that RSA would be secure against it if the public keys were 8 trillion bits. And there are disk drives there'd be disk drives that would be barely big enough to hold an RSA public key, and the calculations would be inordinately expensive. But it could be done as a thought experiment, but in practice we need new algorithms. Right. So we need to replace our public keys with new algorithms. And do we have a separate slide on that? Right. Yes. The RSA would work, but only with 8 trillion bit keys. And right, Grover is not devastating because at best you have to double the key size in order to be able to get there.
Actually, let me talk about it.
You want to talk about this? Okay.
Okay. So, why are we not worried about Grover's algorithm? We're really only worried about Shor's algorithm. So at best, it just means double the key size. You might think that, well, if it makes the work go from 2 to the 128-bit to 2 to the 64-bit, just run it twice or something, and then you'll get down to 2 to the 32. But no, it doesn't work that way. You can only get a single square root. And it's not even as good as that, because a quantum computer has to be slower per instruction than a classical computer. And the reason, as we'll talk about later, it has to run at sort of near absolute zero. And if it does any work, it generates heat. So you can't have it think any harder or any faster than you can cool it down to the millikelvins of temperature that it has to be at. Also, parallelism doesn't help as much. So with a classical computer, you can use 1 million computers and in parallel, and it will make the answer happen in 1/millionth of the time. But with Grover's, as we'll see on the next slide, if you're going to parallelize the search of keys of size 128 bits, if you have 1 million classical computers and you give each one a share of the key space, so you give each one 1/1,000,000th of the keys, 20 bits is 1 million. So you only need to search 2 to the 108 keys, which means that it will be 1,000,000 times faster because you have 1 million computers. But if you have 1 million quantum computers running Grover and you gave each one 1/1,000,000th of the keys, that would mean each one only needs to search 2 to the 108 keys instead of 2 to the 128, which would mean that with Grover's and the square root, then each one will take 2 to the 54 time instead of 2 to the 64 if it was a single one. But that's only 1,000 times faster than it would have been to do a single quantum computer. So interesting trivia. Elliptic curves is another public key algorithm that is very popular, especially in cryptocurrency. And it's security equivalent to RSA, but with much smaller keys. So for instance, a 256-bit elliptic curve key is equivalent to a 3,000-bit RSA key. But the size of a computer, a quantum computer, necessary to break a key of a particular size is sort of depends on the size of the key, not the algorithm so much. So it will be way sooner that there will be a quantum computer capable of breaking 256-bit elliptic curve keys than 3,000-bit RSA keys. So as a result of that, the fact that elliptic curves has smaller keys and can be attacked with Shor's algorithm on a quantum computer means that people are now saying, don't bother converting anything to elliptic curves. Wait for these new replacement algorithms that we'll be talking about and convert to that instead. So yeah, there's a debate about when and if real quantum computers will exist. We have basically toy things now, but for actually breaking cryptography, we're way long away from it. If you get a bunch of people in the room and you say, when will we have it, you'll probably have some people that will say, 10 years, and you'll have other people that will say 300 years, and other people will say never. No one really knows. But since we can't prove that there never will be a quantum computer capable of breaking, 3,000-bit RSA keys, we have to convert away from those, because if suddenly somebody had one of these things, suddenly everything on the internet could be impersonated, or all of the cryptocurrency could be stolen and spent. So we don't want to be surprised by that. So we are going to have to convert, and then you'll find you have a bunch of customers that will basically, in some number of years, they'll basically say, no, if your system has any of the current public key algorithms, we're not going to buy it anymore. So long before quantum computers actually will be a threat, we're going to have converted. So what they taught, the new algorithms are unfortunately called post-quantum cryptography, which is a terrible name. What people hear, I notice, my colleagues, it's like, oh, well, quantum computers are like such a complex field, and then post-quantum, oh my goodness, that's right. So these are just normal algorithms. They really should be called quantum-safe algorithms. They're just normal public key algorithms, but would not be attacked by Shor's algorithm. But unfortunately, the world is calling them post-quantum algorithms. So yeah, people get confused thinking that a post-quantum algorithm is after the world has converted everything to quantum computers, you'll use these algorithms instead or something. But it's just a bad name. Yeah, a typical quantum program, suppose you want to do a brute force search for an n-bit key. So you know that you're using 128-bit keys, and you know a particular pair of plain text and ciphertext, and you want to know which key encrypted this plain text to get this ciphertext. So you can do a brute force thing and try all to the 128-bit keys. But on a quantum computer, what you would do is you would start with n qubits, you'd initialize them all to 0, then you'd run this magic Hadamard gate on each one of them. And so now all 2 to the n, I mean, if there were 128 of these qubits, now all 2 to the 128 possible keys are being represented, superposed equally on these 128 qubits, with equal probability. So what you want to do in order to do a search on a quantum computer, and this is how Grover's algorithm works, is you do something that makes the probability that if you read the qubits more likely to read the special key that maps this plain text to this ciphertext. So with Grover's, what you have to do is you have to do that magic step 2 to the n/2 times. So if it's a 128-bit key, you have this magic operation that you keep doing, and then after you've done it 2 to the 64 times, and you read it, you'll almost certainly get the answer you want. And you know, it's really clever how it actually boosts the probability of the answer that you want without reading the qubits and all that kind of stuff. But you know, in one day, there's only so much we can talk about. So let's say that you were to graph the probability, the x-axis will be the amplitude of not being the magic value that you want. So the k is the magic value, the key that actually maps the plaintext to the ciphertext. And the y coordinate is the probability of reading state k. So when you first start out, everything is equal. So you'll be at that point in the circle where you know, the probability of it being not k is sort of the same as being k. But each time you do the operation, it kind of goes around the circle, making it more and more likely. And you hope that you stop when you get it to be vertical. And interestingly, if you're like an overachiever and you do more work, it'll the angle will keep increasing, so it'll get less and less likely that if you read it, that you'll get the value that you want. So quantum computers will be phenomenally expensive and unpleasant to operate because they have to be at near absolute zero. They may never happen, or maybe they'll be here in 10 years. Where I said they, I don't mean like little toy ones. I mean ones that could break cryptography. So there's this notion, yeah, why don't you talk for a while?
Okay. So there's this notion called quantum supremacy, which was sort of somebody invented this as a hurdle that we'll know quantum computers are real when they can solve this problem. And unfortunately, somebody made up this challenge, and unfortunately, the challenge turned out to be easier than they thought it was going to be. What they said was that if you could have an actual quantum computer and show that it could solve some problem that you can't could do some computation that you can't feasibly do on any classical computer, well, then you've proved that the quantum computer is good for something because you couldn't have done it on a classical computer. And Google achieved this and made a big splash in the news. But they did that by cleverly creating the problem, which is they said, they built this 53-qubit quantum computer, and they said the problem that we're going to try to solve is what would a 53-qubit quantum computer do if we gave it an arbitrary program? And their physical box, the 53-bit quantum computer, could in fact calculate that, but it was impractical to simulate that on a classical computer in any reasonable amount of time. And so it is a problem that you can solve on a quantum computer that you can't solve on a classical one, but it's not one that anybody would care what the answer was. A sort of more interesting thing is when somebody, factors some large number that nobody's ever been able to factor on a classical computer. That would say something because it's a problem that comes out of a real space. This quantum supremacy doesn't really mean anything. There are various ways that you can plot the progress, and people are making advances. The quantum computers keep getting better by various metrics. One of the things that people have made analogies with is with Moore's law, and we watched integrated circuits get more and more dense, and it was the famous line that it's doubling every couple of years, off into the arbitrary future, and we followed that for a long time. That computers got cheaper and they got faster, but one of the variables that went in there that is not often mentioned is that the amount of dollars that went into R&D funding for chip research also doubled every year for a large number of years. And yes, quantum computers may well develop on that timeline, but only if we keep doubling the amount of money we're investing in quantum computers. And the problem is, how much money are we going to invest in quantum computers before there's any payout from it? And so until somebody finds some application that will pay for the development of these things, it all becomes research funding, and research funding doesn't keep doubling for a long time. But what will definitely happen is that people will worry about somebody having a quantum computer. People are already worried that, yeah, maybe Google doesn't have a quantum computer that can do this yet, but maybe NSA has secretly built a quantum computer that they can break RSA with, and they just haven't told us about it. And as long as people are worried about that, there's going to be a lot of pressure to migrate away from RSA and ECC onto quantum-safe algorithms. The new replacement algorithms are normal algorithms that run on normal computers. And NIST is leading an effort right now to, in fact, standardize some. There's been a lot of academic research on them for years, but it's been sort of disorganized, and they're trying to organize it and actually bring these things in and have them compete with each other and try to standardize some. There isn't going to be a single best algorithm, and the reason for that is because unlike RSA and, ECC is almost optimal. It's sort of the keys are only a little bigger than theoretically the best that they could be. These algorithms all have problems of one sort or another. Some of them have enormous public keys. Others might have reasonable sized public keys, but they're a lot more computation than the old algorithms were. Others still might have reasonable-sized public keys, but they have enormous signatures. And all of them that have been worked on so far can either do signatures or they can do encryption, but they can't do both, unlike ECC, which can do both, and RSA that can do both.
Let me interject.
Okay.
Which is one of the kind of interesting things is, so there'll be like several of these post-quantum algorithms with very different properties, like computation versus whatever. And what's very interesting, if you have some sort of system, is choosing the right one of these algorithms that will most fit your system. So if you know, your system really is very sensitive to storage or latency or whatever, knowing the properties of these algorithms so that you choose the best one for your thing is kind of very interesting. Anyway.
Right, and another thing is that one of the things that in our book we called the fundamental tenet of cryptography, which was that if a lot of smart people have been working on a problem for a long time and haven't come up with a solution, then it's probably a hard problem. And with cryptography, the way people become confident that a cryptographic algorithm is good is when it's been deployed for a long time and a lot of people are using it and a lot of people are trying to break it and they haven't succeeded. And so necessarily there's a problem with algorithms that are new. And in particular, you know, as an example is that NIST, as they've been, you know, narrowing this set down, one of the algorithms that was about to become a finalist, just before that, somebody announced, "Oh, wait a minute, I broke it," and this was a fairly badly, and so people are worried about, well, gee, if I'm not safe with the old algorithms because there might be quantum computers, and I might not be safe with the new algorithms because there might be defects that just haven't been discovered yet, what am I to do? And so one of the things being proposed is hybrid algorithms, and what that means is that if you want to sign something, your public key will have two parts, the quantum part and the non-quantum part, and you'll sign it with both algorithms, and only if both signatures check will you consider the signature to be valid. And that way you're safe unless they both build quantum computers and discover a flaw in the thing. It requires sort of a double failure. And likewise, to encrypt something, I can encrypt it with a conventional, you know, with RSA or some other conventional crypto system, and then take the result and encrypt that with a quantum-safe crypto system. And if somebody breaks one of them or the other, you're still safe. Right, so this was the key recovery attack, right? And this was the quote with the gobbledygook. Did you remove the gobbledygook quote?
Yeah.
Right.
Yeah, so what does it mean that the algorithm was badly broken? This was, you know, like there's all these different families of these things. This one was the isogeny-based algorithm. I could impersonate someone that understands the algorithm, but I didn't really understand it. So didn't bother talking about it in the book, and I was so relieved that it got broken, so that, you know, the fact that we didn't put it into the book. But the original paper on this thing, it's a little hard to read. So it's, you know, for instance, it says, our attack exploits the existence of a small non-scalar endomorphism on the starting curve, and it also relies on the auxiliary torsion point information that Alice and Bob shared during the protocol. So, you know, this is not something you really want to read unless you're into this stuff. But the punchline is that their attack took about an hour on sort of a normal computer, a single core Intel Xeon processor, that given a public key, it could calculate the private key. So that's like really badly broken. And these attacks are, you might think, oh, an attack on these algorithms has to be some sort of subtle quantum mechanical thing. No, I mean, these are breaking these algorithms using classical computers to break them. So yeah, the hybrid algorithms, as Charlie said, that if you want to make sure that your system will be secure, even if someone comes up with a sufficiently large quantum computer, then you'll want to be using the post-quantum algorithm. But if the post-quantum algorithm turns out not to be good, then as long as you're doing both the way you design your system, it requires either one of them being secure. Your system will still be secure. Okay, so qubits are really annoying. So, you know, think of them as hyperactive, friendly puppies. They just sort of want to entangle themselves and interact with anything around them, which means they're going to lose their state. So that's why they have to be at near absolute zero. Just don't give them an opportunity to go play with anything else around. So you have to either have them in a near absolute zero temperature or in a near perfect vacuum. And even under the best of circumstances, if you can do that, they flake out and lose their quantum state. So a quantum computation, in order to be meaningful at all, requires the qubits to keep their quantum state throughout the whole computation, or what's the point if they're just going to be sort of have random values because they flake out or whatever. So the only way that this can work is to do quantum error correction. So even classical computers require error correction. So like there's DRAM memory, which decays. So you write memory and it doesn't stay there. So the computer has to be constantly reading the state and rewriting it before it degrades so much that you lose the information. Well, you can't do that with quantum state because you can't read it. So it sort of has to keep the quantum state, like longer than DRAM would keep its classical state. So this is, like really quite terrifying. So in order to do that, you have to somehow do quantum error correction, which is much more complicated than being able to read it and write it out cleanly. So it's an active area of research, and it's really, really complicated stuff. So what it is that you'd have a group of physical qubits that are all flaky, but they act together as if it's a single well-behaved qubit. And so the clump that's simulating a single well-behaved qubit is known as a logical qubit. And the components in this clump are physical qubits. So when people talk about how many qubits are in that they've built in a computer, they're always talking about physical qubits. They're not talking about logical error-corrected qubits. So how many physical qubits does it take to make a well-behaved logical qubit? Well, it depends on how stable the physical qubits are. And there's all these different technologies people are, trying out to make qubits that will be more stable. And the other is how long the computation will take. So, right. So I'll let you talk for a while.
Right. In terms of, one of the properties of qubits is that they're like radioactive particles, that they have a half-life. So it's a matter of even under the best of circumstances where you've done absolutely nothing wrong and the qubit has no opportunity to interact with anything, there's still some half-life that, it might be an hour, that there's a probability, of a half that it'll decay before that happens. And so, right, so it's really important that you put these things together. One of the challenges is not just building a logical qubit to be able to preserve its state for longer. For that, I think, you could build, I think they've identified a way to put 9 physical qubits together into a logical qubit and read it in some, weird way that allows it to maintain state for longer. But remember also that we're applying gates to these qubits. And so you have to have a way to apply if you have a gate that you wanted to apply to 2 qubits, you have to have a way to apply that gate to 2 logical qubits. And oftentimes that involves building a whole lot of other gates and auxiliary machinery. So in fact, the reality is that in all the quantum computers people have built, nobody has managed to build even a single logical qubit for which a universal gate set can be applied. Well, I guess you'd actually have to have 2 of them before it would be interesting. But this is one of the steps that we're going to have to reach moving forward.
Oh, okay. So we're behind
Right.
on time, I think.
Okay. So yeah, it's an active research area to get error correction to work and to get make the qubits be more stable. One of the issues about quantum error correction is that when you're doing the error correction, it actually requires that you do a computation. So if you have a set of qubits and you want to sort of refresh their state, you're going to have to do some calculation with them. If the error rate is high enough, you're going to introduce more errors than you're going to correct in the error correction stuff. So you have to. So there's a certain threshold low error rate that you have to have before the error correction will even help. And then once you get below that. Once you get below that, then the logical qubits have fewer errors than the physical qubits, and you can in fact build multiple layers of hierarchy to build, logical qubits out of logical qubits to get the error rate even lower. But again, you have to hit the threshold with the physical qubits, and then, yeah, once you reach that point with hierarchy, you can get the error rates as low as you want. However, each level of hierarchy, you have an exponentially growing number of physical qubits to make up each logical qubit. So the current state of the art is that they built quantum computers with 50 to 100, physical qubits, and that's been increasing over the last few years. The error rates are as low as 0.5% per gate, which, if you think of that in terms of what that would be like on a conventional computer, that would be absolutely horrible, because the error rates, is one in 10 to the 23rd or something like that. But 0.5% is low, and it's almost low enough that a logical qubit would actually benefit. So they're almost there, but they have to improve that some more in addition to the logical qubit things. Nobody's ever managed to do that yet. And so we need to improve the error rate, and we need to vastly improve the number of qubits that we can put in a quantum computer. And the progress is slow, but there may well still be some breakthroughs that allow people to make vast expanses. People have said there's theoretically no reason why we couldn't get the same density on on qubits as we have on conventional memory, where you've got enormous numbers packed into a very small space on a chip. But again, somebody has to figure out how to do that. And there's another class of quantum computer called an annealing things, and D-Wave is a brand name of a company that's been doing that for a long time. And they get much larger numbers of qubits. However, they don't implement a universal gate set, which means that the set of problems they can solve is different and harder to analyze and compare. They'll probably never be able to build anything that would be useful for factoring numbers, but they have things that they claim are useful for other things. Okay, Shor's algorithm. How do you want to?
Well, all right, I'll talk for a while. Yeah, so this may bleed into the second half because, yeah, whatever. You guys are the first people that we're doing this talk with. So, anyway, so Shor's algorithm factors numbers, and it also solves discrete logs. Now, it doesn't matter what discrete logs are, but like the Diffie-Hellman algorithm depends on that. But for now, let's just concentrate on factoring numbers. So who cares? Well, because our current public key algorithms, RSA depends on factoring being difficult, and Diffie-Hellman requires discrete logs, whatever they are, being difficult. I say whatever that is because we don't need to focus on that now. So public keys, secret keys, and hashes, what are they used for? Well, secret keys, like the AES algorithm, are used for bulk encryption. Public keys are used for digital signatures or signing code or authenticating and establishing a secret key, like with a protocol like TLS. Hashes, you tend to sign a hash of a thing rather than signing the thing itself. Quantum computers only threaten the public key algorithms. As I said, hashes and secret keys are fine as long as you go to 256-bit secret keys or 512-bit hashes. So, for example, for blockchain, we might as well talk about blockchain because it's a blockchain conference. The proof of work blockchains depend on hashes being secure. So quantum will not be a problem as long as they're using big enough hashes. But proving that you own a piece of cryptocurrency depends on elliptic curves, which would be broken by Shor's algorithm. So we'd have to, we'd have to convert from that. So let's see. So at this point, we have like 4 minutes. I'm wondering if we should defer starting this until after lunch.
You can certainly talk about modular arithmetic.
All right, I'll talk about modular arithmetic. So real numbers are annoying to represent on a computer. Like how many bits do you need and whatever. Even if it were integers, it gets annoying if you're doing arithmetic with integers because integers can get arbitrarily large. So cryptographic algorithms tend to use modular arithmetic. Now, what is modular arithmetic? It's sort of like a clock, an analog clock, if some of you might be too young to remember those things, where there are 12 numbers, and when it gets, past 12, it starts again at 1. So with modular arithmetic, it's an integer that is between 0 and 1 less than the modulus, and you just do ordinary arithmetic on it, and then the answer, if it's not in that range, is you divide by the modulus and take the remainder, and that's how you compute with modular arithmetic. So reviewing RSA, the RSA algorithm. An RSA public key is a pair, n is the modulus, and e is the exponent, and that's the public exponent. And to encrypt something with an RSA key, so to encrypt M, you compute M to the E mod n. So that's the encryption with RSA. And to the private key is a different exponent, D, and the same modulus. And so, we came up with the term, they're exponentiative inverses, E and D, because you exponentiate by one, and then you exponentiate by the other one, and it undoes it. So, mathematicians get upset because there is no such, they don't use the term exponentiative inverses. And so, when they complain at me for using it, I say, fine, do you have a better term? And they say, well, no. I say, well, then I'll keep using it. Everyone knows what a multiplicative inverse is. Or an additive inverse, but an exponentiative inverse mod n is two different exponents that cancel each other out if you exponentiate by one and then exponentiate by the other. So, m to the e mod n, if you have something that's encrypted with the public key and then you apply the private key, it means you raise that to the power d, which means you get m to the e times d, and the e and the d cancel each other out, and you'll get back to m. Okay, so that's basically what RSA is, a sort of a review of that. You think well, I could do the relevant background. I think I could get through that.
But there might be new people joining, and they probably want to hear the background.
Oh, well, okay.
It's already time.
Okay, I suppose. Though my watch says that I have 1 more minute. I should actually have stopped for questions. But yeah, how you guys doing? Oh, right. Okay, so let's just make sure that we start again promptly at 12:15 because the 1:15. We could start at 12:15. We'd have more time. Yeah, so the thing about other things that I want to get to, after Shor's algorithm, I'm explaining what does a quantum algorithm actually look like, and boy, is this one cool. We'll actually talk about what some of these new public key algorithms look like. So, if you read the actual specs, it just is very mysterious. You do these things to these polynomials and stuff, and there's no real intuition there. So we're going to try to give you intuition so that you feel you understand it. So anyway, so that will be after lunch. So, thank you, everyone.